First, I would like to thank the SERI organizers for the exciting lineup of research talks and for giving an opportunity to software engineering R&D group in Accenture Labs to present our early research outcomes in responsible software engineering. I'm joined by my colleague Vibhu Sharma in this talk. While notions of responsible AI is a topic of great interest, we take a broader view of what makes software responsible. Now, before we get into the details of the research, I will use a few examples to illustrate why the broader view is important. At Accenture Labs, we are working on realizing a responsible software engineering framework. I will spend a few minutes on explaining the framework. Vibhu will take over from me and get into the details of the research we are conducting in Green ML and talk about some of the exciting early results. Over years, software design focused on aspects like modularity, which in a way are intrinsic quality of any software. However, we now see two important trends. First, as AI becomes central to most software applications, the likelihood of an improperly designed AI deepening existing biases or even creating new inequalities is quite high. In the example here, it was observed that an AI model could recognize a man as a woman just because the photo is from a kitchen. This is a classic case of reinforcing gender stereotypes. The second trend pertains to the massive adoption of digital systems based on cloud, blockchain, and other technologies. Here, even the small energy inefficiency in the software system architecture can be amplified greatly, leading to a severe impact on the environment. One of the studies conducted in 2015 on global data center electricity consumption predicted a very dire situation. Discussion on the exact models and extrapolation techniques aside, numerous studies have shown the significant environmental impact of data centers. A recent study on carbon emission equivalent from training large AI models found a significant negative impact on the environment. All these examples suggest that software engineering now needs to adopt responsible design principles to mitigate risks to individuals, societies, and the planet. At Accenture Labs, we are conducting research to identify design and development principles that will lead to responsible by design software development. To look at this in a holistic manner, we have defined a framework called the ROSE framework that allows us to pose questions related to specific responsible principles and also identify trade-offs that engineers would have to consider when building software. The people dimension is about how to design software that individuals can trust, which means being transparent about the purpose of the software, using their data for exactly the purpose it is designed for, and being fair. People dimension also calls for the software to be inclusive and accessible so that it does not promote economic, social, and political inequalities. The planet dimension is about developing green and environmentally friendly software. We will take a more detailed view in the remainder of the talk. The organization aspect deals with the intrinsic sustainability of software. How should software be designed to be resilient and adaptable? Intrinsic sustainability makes us think about designing software that can evolve over time without incurring significant costs of re-architecting and development. Adopting responsible software principles can lead to newer forms of technical debt, and new metrics and techniques are required for managing that. Finally, it covers the tools, methods, incentives that engineers need to have for developing truly responsible software. Interesting trade-offs also emerge while adopting responsible software principles. For example, when designing highly energy-efficient software, does the choice of programming languages or frameworks lead to a greater intrinsic complexity of that software? The framework helps assess and manage trade-offs where required. Now that we have seen the glimpse of the framework that we are working on at the labs, I will now hand over to Vibhu to talk about our work in green software and green ML.
Thanks so much, Vikrant. Hi, folks, I'm Vibhu. Now, there are important decision points throughout the software lifecycle wherein trade offs exist between business goals and metrics and sustainability goals like energy efficiency. In the green software engineering R&D, we are exploring different substreams of research wherein interesting intersections exist between various software lifecycle design choices and energy consumption. In green ML, we look at the interplay of various different machine learning parameters like the epochs of model training or data size considerations or data quality issues on the consumption of energy. We will delve deeper in this particular aspect today. In green engineering, we are looking at trends of how certain programming languages could be more energy efficient than the others for specific programming tasks, and also how certain platforms and libraries could have configurations which are more energy efficient. The area of green mobility is interesting because the way one uses applications on their devices like smartphones, or essentially the digital habits of the users, have significant energy implications, and therefore personalized recommendations can help individuals reduce their energy footprint. Similarly, in the area of cloud computing as well, there are interesting trade offs between various deployment and migration policies and other metrics like performance and reliability with respect to energy consumption of the workloads on the cloud. Finally, the way we code and design our software systems and the patterns thereof have a definite impact on energy efficiency, and that is also an important area of R&D for us. So let's start with green ML. Now, do you know how much energy does your machine learning model consume? Well, research literature around life cycle assessment for AI shows that there is significant amount of energy that is used in training AI models. And this energy consumption is increasing exponentially over the years. That forms a key motivation of some of our experiments in this area. Our goals are to study how different aspects in machine learning, like the size of data sets, the number of training epochs, quality of training data, and other such parameters affect the amount of energy consumed in the machine learning lifecycle. And are there important decision points wherein we can take informed decisions based upon energy and accuracy trade offs? In this first experiment that we discuss here, we explored the effect of training epochs on the energy consumed in machine learning. For this experiment, we took a very well known but rather small dataset called the Fisher's iris dataset, which is a multivariate dataset introduced by the British biologist Ronald Fisher in 1936. There are three output classes here with 50 samples each for the three types of iris flowers. And there are four features in this particular dataset. Now the figure on the bottom shows the approach we have taken across all our experiments, where we use the Intel Power Gadget to measure energy across a particular period of interest. In this case, the energy consumed across epochs of training. For this particular classification problem, we used a neural network model with two hidden layers. So essentially a very small model. So here are the results for this particular experiment, averaged across 5 different runs. In the graph on the left hand side, you can see the number of epochs of training on the x-axis and the average cumulative energy used on the y-axis. In the graph on the right, you see the average accuracy on the x-axis and the average cumulative energy used on the y-axis. Now, while you can see that there is an increase in average cumulative energy as the number of training epochs increase, which is obvious, we also see that the relationship between the increase in accuracy is very non-linear when we compare it with the corresponding increase in energy usage. For example, we only need about 964 joules of energy to reach about 96% accuracy. And then the model takes another 2815 joules for the next 1.74% increase in accuracy. And then for a minuscule 0.08% of accuracy improvement, the model training consumes about 4705 joules. So what you can see here is that while you need only 964 joules to reach an accuracy of 96%, by further continuing with the training epochs, the model will consume more than 15 times more energy for the next 2.5% improvement in accuracy. So the question is really for us to decide whether that 2.5% improvement in accuracy justifies a 15 times more energy usage. Using insights like these, one can take informed decisions to create go-no-go gates, as we have tried to show on this particular slide, so that one can choose to stop when the accuracy is acceptable and thereon prevent a significant amount of wastage of energy for very small or minuscule improvements in accuracy. For our next experiment, we study the effect of training data size on deep learning model. In this case, we have taken an image classification problem based upon a publicly available dataset, which consists of images of natural scenes from around the world. There are 6 classes here, and the number of training examples is about 14,000. In this experiment, we divide the training set into 10 different subsamples or subsets with sizes as 10%, 20%, 30%, and so on of the total training data set. So essentially, we have 10 increasing subsets of the overall training data set, which we use for different runs of model training. We have used a convolutional neural network here with 2 hidden layers as our model of choice. Now note that as part of each experiment, we train the model from scratch using each of the training data subsamples. That is, there are 10 model training sessions in each experiment, and these results are essentially averaged across 5 such experiment runs. As previously, the graph on the left shows how energy is consumed as we increase the training data set subsample size. And the graph on the right shows the relationship between the accuracy achieved by the model for the increasing sizes of training data subsamples versus the cumulative energy consumed, which is on the y-axis. Now we again find that the relationship between accuracy and energy is non-trivial here. We can see that after reaching about 64% model accuracy, we need about 84,600 joules of energy for the next 10% increase in accuracy. But then more than 87,000 joules for the next 0.82% increase in accuracy. So essentially, if we would have used all the available training data set in this case, assuming that consuming the whole training data set is always better, we would have consumed almost 47% more energy during model training than the amount that would have been required had one used only 70% of the training data set. All this for a validation accuracy trade-off of less than 1%. So this is again an interesting example of how such insights are important to take informed decisions in the machine learning lifecycle. Well, there is one clear result here. we can make machine learning green. Our experiments show us that it is possible to take energy efficient decisions in the machine learning lifecycle while optimizing important characteristics like accuracy. This also provides opportunities to create multiple go no go gates during ML DevOps. Approaches are needed to create visibility to such machine learning trends to all the stakeholders involved so that they can make these important and informed decisions which help in the cause of sustainability. Think about all the energy you can save even while training small machine learning models, which can help light up rural homes or help in reducing the carbon footprint of machine learning across the world. Well, we at Accenture Labs are continuing with more such experiments in this and other areas of software engineering, and we hope to share some of those results and insights very soon with all of you. Thank you.
Thank you, Vibhu. This brings us to the end of our presentation. We look forward to your comments and questions and discussing more on these topics. Once again, thank you to the SERI organizers and the audience for listening to our talk.